Today I'm going to show how to solve the longest common substring using the suffix trie approach. Okay, there are many approaches to solve this problem. You can use DP, but today I'm going to show you how to solve it using the suffix trie. Okay, so we are going to use suffix trie to solve this problem. Okay. So the problem statement is, suppose you are given two strings, okay, x and y, and you need to find the longest common substring. So for example, if x is equal to xa, bxa, and y is equal to ba, bx, ba, right? So here the longest common substring is ABX between both of them, right? Okay, so with the suffix trie approach, you already know, right, that the suffix tree represent the substrings. Why? Because all the substrings, right, they are a prefix of suffix. Now, if you don't understand this, I would say please watch my video of suffix trie pattern searching algorithm. Okay, so now let's say suppose you have let's take the example of string x, okay, and let's get all the suffixes of string x, right? So it will be a, and let's append the ending character $8, then x, a, sorry, pound, hash, whatever you say, bxa, hash abxa, hash xabxa, hash. So these are all the suffixes. Now for the string x, okay, the substring of string x um are x, xa, xab, xabx. So these are the substrings of string x, or maybe a, ab, abx, right? So all the substrings, they are a prefix of this suffixes, right? Because usually, I mean, this suffix, right, they start at 0 with 1, I mean, 0, 1, 2, 3, 4, all the different index position, and they end at the very end of the string, right? So this substring, right, any substring that you see here, any substring of x, right, they're a prefix of the suffix, because any substring will start with either of this index between 0 to 4, and it's gonna end at the end of the string, or it's gonna end before, doesn't matter. But if it starts at 0th index, it might be a substring, the substring might be a prefix of this. If it starts at index 1, the substring is starting at index 1, anything a, b, a, b, x, whatever. So that's the prefix of the suffix, right? That substring is a prefix of this suffix, right? So all the substring a, b, a, b, x, a, abx. So all the substrings, right? They are a prefix of this suffix, and all this substring b, bx, bxa, they are a prefix of this suffix, and all the substring x, xa, they are a prefix of this suffix, and all the substring a, and here all the substring x, xa, xab, xabx, xabxa, they all the substrings, they are a prefix of this suffix, right? So there was a logic, okay, behind this, that why the suffix, if you create a suffix tree, it gives you all the substring, okay. Now let's write the suffix of string y, which is a dollar b a dollar x b a dollar b x b a dollar a b x b a dollar b a b a b x b a dollar, right? So those are the suffix of the string y, right? Now to find the longest common substring, what you are going to do is you are going to construct the generalized trie out of these two strings suffixes. So we're going to create a common trie for both of the suffixes. And to find the string which is a common and which is the longest between both of the string is you need to collect the dollars and the pound, and if the node has both dollar and the pound, that means it considers itself as a common. I'm common between both the string and it appends itself to the longest string that has been found so far. So now um, let's walk through, okay, this approach, okay. So let me write here all the suffixes, okay, for string. Okay, so that's the string y, and the sorry, that's the string x, and the suffix for all the string x is a pound. Then we have x a pound, and then we have bxa bxa pound. Then we have abxa abxa pound, and the other one is x a b x a pound, okay. And the suffixes of y is a dollar b a dollar x b a dollar b x b a dollar a b x b a dollar, and then b a b x b a dollar. Okay, now we're gonna create a generalized suffix trie. So for that, let's say let's do this. Okay. Okay, let's create a trie. So then we have this root node, and then the first one was a pound, right? So we have this a, and then we have this pound. Okay. Then the second one was xa pound. Okay. So we have this x, and then we have this a, and then we have this pound. The third one was bxa pound. Okay. It was bx a pound, And the fourth one was ABXA pound. So ABXA pound. And the fifth one was XAB XA pound. Okay. Okay. Now let's enter the suffixes of the phi, which was a dollar, right? Then be a dollar. So be a dollar. And the next one was XBA dollar. So XBA dollar. Okay, XBA dollar. And then BXBA. Okay, so BXBA dollar. So it will be BXBA dollar. Then it was ABXBA. So ABXBA. Okay. ABXBA dollar. Okay. And then BXBA. Okay. BXBA. So BXBA. Okay. Then there's a BABX BA dollar. Okay. Okay, so now our trie is constructed, suffix trie for both the strings. Now what we are going to do is we are going to see traverse it using the DFS. We are going to count the dollars and the hash, and if we have more than $0 and 0 hash, then we'll consider that I'm a common, so I'll add myself to the longest string. Okay, so let's start the DFS from this node. Then we go to a dollar. So once we reach this dollar, we know that we have $1, 0 pound, and the string is empty. Okay, so this is going to return $1, 0 pound. Now this one, right? That is $0, 1 pound. Then it goes to B, X, B, a dollar. Okay, so this is $1, 0 pound. It's gonna come to $1, 0 pound, and it will not append itself because we need to have more than $0 and pound. Okay, uh, if we have both pound and dollar, then only a is considered common. So same here, $1, 0 pound. Here's $0, 1 pound, $0, 1 pound. But here we have 1 plus 0, $1, 1 pound, and X will say, oh, I got more than $1. I got dollar and pound both. So I'm common. I'm gonna append myself. Same with B. B will say, okay, I have more. I mean, I have more than $1 and $0 in pound. So I'm common. So it will append itself. So it will be 1, 1, and BX. Okay, BX. Okay, and A will say, okay, now I have 1 plus 0 plus 1. So I have $2. And then 0 plus 1 plus 1, 2 pounds. And I'm common. So I'm going to append myself to the longest common substring. Now the longest common is BX, so ABX, okay. ABX, okay. Okay, then it goes here X, A. So here it is $0, 1 pound. Here it is $0, 1 pound. A will say, oh, $0, 1 pound. X will say $0, 1 pound. B will say $0, 1 pound. Now 0 plus 0, so this will be $0, 1 pound. It goes here, this is 1 0, XBA, right? So that's 1 0 1 0. So here this is 1 0. So it is 1 1, okay? 0 plus 1 and 1 plus 0, so 1 1. So yeah, I have $1 and 1 pound, so X will append itself. So X and then 1 comma 1, okay? So X will append itself here. Now then there is a BXA pound. So that is $0, 1 pound, $0, 1 pound. So here it is 0, 1, 0 and 1. This is $1, 0 pound. Same, it will come here $1, 0 pound. So this will say, oh, I got $1 and 1 pound. So 1, 1 and X. I'll append myself. Right? So here be a dollar. So $1, 0 pound. Here also $1, 0 pound, and here also $1, 0 pound. So there is no pound. $1, 0 pound. So now here it is $2 and 1 pound. So we will say yes. I have more than $1 and 1 pound. So I'll append myself. So this is $2, 1 pound, and BX. Right? So the longest common substring between these two string, right, is ABX, right? That's the longest common substring, right, between the two strings. So we need to return the longest one. So once it's at the root node, right, we're gonna see, okay, so 2, so it's a 3 plus 1, that is a 4. So this is 2, right? This is 2. This is 2, right? So 2 plus 1 plus 2, so $5. 2 plus 1, 3 plus 1, 4 pound. And the longest is ABX. Okay, so that's our answer. Now, let's try to implement it, okay? Let's try to implement it, okay? So let's write our approach first, what we are going to do. The approach is we are going to build generalized suffix trie for all the suffixes, right, of both the strings of x and y. Then, sorry. Then after building the suffix trie, what we are going to do, we are going to count dollars and hash, and if there are more than $0 and hash, then I am common, and I will append myself to the longest substring. Okay, what is the time complexity of this approach? What is the construction time for the suffix, right? So for the string x, suppose the length is n, then there are n suffixes. The max length of the suffixes is also n, and the insertion time or the creating the suffix trie for string x is n square, and for string y, if suppose the length is m, then construction time is m square, so n square plus m square. That's the construction time. So the construction time is equal to n square plus m square. But you know, right? You can reduce this construction time to linear using the Ukonnen's algorithm. Using Ukonnen's, you'll have construction time of n plus m, right? So that's the construction time. What is the time for getting the longest common substring, right? So what we are doing the DFS, covering all the nodes, and we have n square plus m square nodes, right? So that time is also O of n square plus m square, but using Ukonnen's, this is also a linear. Ukonnen, this is also linear. Okay, so basically the suffix trie gives you the linear time complexity. It's only like you need to use the Ukonnen's algorithm. Just mentioning is fine in an interview. It's hard to implement it. So what is the space complexity? So each n suffixes max length n, so n square nodes, so n square plus m square nodes. So O of n square plus m square. Okay, so now let's try to implement. Okay, so let's make a trie node. Okay, so you need a trie node for this. So public class trie node. Okay, what is a trie node? It contains the character and a children. So public hash map character trie node children, and then it also contains the end of word, public boolean end of word, the constructor public trie node end of word is equal to false, children is equal to new hash map, constructor done, the class done. So that's the trie node. Now, once you're done with the try node, let's write the actual implementation. Okay, so we have a public try node, that's our root node, and then we have public string longest common substring, and then we have a string s1 and string s2. You need to find the longest common substring. So what you are going to do is build suffix trie from s1 and s2. Once you are done building the suffix trie, you return get longest common substring. We are going to pass the root of a trie node, and then we are going to do a TFS, right? So we need to pass the node, and then for the root, the character is nothing. So we'll just say that it's a star, just to recognize that that's a root node. So the star character, I mean, it doesn't have any character, but and then we need to return the longest common substring, right? So what this function will return, it will return something like this. It will return the longest common substring, the number of dollars, and the number of hash. So it will return something like this. And we're gonna return it in a pair object. So it will the pair, and this will be the pair of string and the array of integers. So return it something like this, and we need to get this abx and return that. So that will be get key, and this will return abx. Okay, okay, now let's build the suffix trie for both the strings. So public void build suffix trie string s1 string s2. Okay, so before building the suffix trie, we need to initialize the root, which is a new trie node with no character, empty root. Okay, so all the suffixes of s1, so for all s1 suffixes, we'll try to insert all the suffixes of s1. So for integer I is equal to 0, I less than s1 dot length I plus plus. So the suffix, it starts from an index position and it ends at the end of the string. So we are going to insert s1 dot substring starting at different ith index, and for s1, let's say the end character is dollar. So that's the end character for s1, and then now we are going to insert all the s2 suffix. So all s2 suffixes. So for integer I is equal to 0, I less than s2 dot length I plus plus, and we are going to insert s2 dot substring I comma, for all the s2 suffix the end character is pound, and there we are done with the build suffix trie, but we still need to implement the insert method. So we are going to implement that public void insert. So here we have our word to insert, and we also have the end character. So trie node current is equal to root, right? So we are going to start from the root. We are going to look through the each character of the word that we want to insert. So I is equal to 0, I less than word dot length, I plus plus. So the first character ch is word dot character at I. So that's the first character. Now we'll see if it's already there. So trie node is equal to, let's see if it's there in the current children. Current children dot get ch, right? If it's not there, then we're gonna insert it. So we're going to create a new node, new trie node, and then we are going to add it to the children. But if it's already there, then we'll move forward. So we'll just have our current point to the node, and we'll keep doing this. So we are done. When we are done at the end, we need to add the end character. So current will be the last character of the word. So current dot children dot put, we are going to add the end character, and we are done with the insert. Okay, so now we are done building our suffix trie for both the strings. So now we are going to find the longest common substring. Okay, so um, public, and we are going to return the longest common substring and the total count of dollar and hash. So we are following a DFS approach. So it would be a recursive DFS. So public, we are returning a string, an integer array for a dollar and a hash count. So get longest common substring, and then we have a trie node, which is our current node, and we have the character ch for that node. For root, we are just adding some random character, star or something, just to identify that it's root, and we don't need to append that character. So now we are going to do the DFS. So integer, let's initialize the counters. Integer dollar count is 0. Integer hash count is also 0. And let's initialize the string as an empty string. Longest common substring is equal to empty string. Okay, so now we're going to start the DFS. So we are going to iterate through all the children of the first current node. So map dot entry, and then we'll have a character trie node, and that's a child. So current dot entry set. Okay, current dot children dot entry set. Okay, so now we have the first child of the current. So let's see now what happens if child, I mean, we have traversed to the end of the node, right? And now the child that is there is dollar or a hash. So child dot get key, I mean get character is equal to dollar. What you do in that case? You just add the dollar, increment the dollar count. So dollar count is equal to dollar count plus 1. Okay, what if the child is hash? So child dot get key if is equal to hash, then you increment the hash count. So hash count is equal to hash count plus 1. But what if the child is actual node with a character in it, right? So if that's the case, you need to do a recursive DFS call, right? So this will be a recursive DFS call for its child, right? And what is it going to return? It's going to return pair of string integer pair is equal to get longest common substring, and then what are we passing in this function? Child dot get value and child dot get key. So that's our trie node and child dot get key with the character. So once we are done with the recursive call, right, we need to see, I mean, once we are done with the recursive call for that node, we need to add the dollar, update the dollar count and the hash count. So dollar count is equal to dollar count, and that will be the zeroth index, the value in the zeroth index for the array, integer array. So pair dot get value that will give you the integer array, and its zeroth index will have dollar count. Similarly for hash count, it will be at one index. Right, so we did this addition, and then now let's update the longest common substring. Okay, so update longest common substring. Okay, now if pair dot get key dot length is greater than longest common substring dot length. If that's greater, then we're gonna update it. We're gonna update the longest common substring is equal to pair dot get key. If you find any longest common substring, right, we're gonna update our longest common substring. Now we are done with this if, we are done with the else, and then we are also done with the DFS follow. Okay. So once we have processed all the children for the current, right, and we got a dollar count, the total dollar count and the hash count, we need to check, I mean, if that count is greater than zero, if the count of dollar and the count of hash both are greater than zero, then we need to append myself. I mean, that means the current node is a common. So I'm common if I have both dollar and a hash, and then I'm going to append myself. Okay. So that's what we are going to do. So we are going to do is, so let's see. So now I am common. I mean the current node, right? The current node and the character. If I have both dollar and hash, and remember, if the current is the root node, right? Then you nothing need to append, right? For root node, okay? So if dollar count is greater than zero and hash count is greater than zero, and it's not a root node, okay? So you just need to check for the character that we have passed in. So that character should not be equal to star, otherwise it's a root node. We are not going to append the star. So the longest common substring for all the children that we have found, right? We need to add this character of the current node if that is common, if it finds itself to be common. So character plus longest common substring. And there you go for root. So for example, let's say we are passing in the root, the very first node. So we are iterating through all the children of the root. Then we are finding the total dollar count, total hash count, and we are also finding the longest common substring. And then we are appending the character of the root if there is any. I mean, for root there is no character, but we need to append the character if it finds that I am common. If I have both dollar and hash, then I'll append my character. So what are we gonna return? Return new pair. We are going to return this longest common substring, and then we also going to return the dollar count and the hash count, right? So new integer dollar count hash count, right? And there we are done. So that's how you implement the longest common sequence. um, Keep watching my videos. I'll cover more problems on tries. Thank you so much for watching.